An additional primary protector is not required at the point of entrance to the house. The pedestal is considered to be part of the structure served, as defined in Article 100 of the National Electrical Code, or NEC. Therefore, the primary protector installed on the pedestal meets the requirement of 800.90 B to be in, on, or adjacent to the building or structure served. Since the run from the pedestal to the house is an inter-building circuit that is less than 140 feet in length and run underground using shielded cable, it does not require a primary protector at each end according to 800.90. Therefore, a single primary protector installed on the pedestal is sufficient to protect the telephone service. Let's delve deeper into the specific sections of the NEC that govern this installation. Article 100 provides definitions that are crucial for understanding the intent of the code. The definition of a structure is key here. The NEC doesn't explicitly define a pedestal as a structure, but its function and purpose in housing and protecting electrical or communication equipment make it an integral part of the overall service. Think of it as an extension of the building service equipment, even though it's physically detached. Section 800.90 addresses the protection of communications circuits. This section aims to prevent dangerous voltages and currents from entering a building via communication cables, which could pose a fire or shock hazard. Paragraph B specifically states that the primary protector must be located in, on, or adjacent to the building or structure served. The intent here is to ensure that the protector is readily accessible and can quickly interrupt any fault current before it enters the building. In this case, the pedestal, being located street-side and housing the NIU with an integrated primary protector, meets this requirement. It's considered adjacent to the structure because it's directly connected to the building's service via the underground conduit. Now, let's examine 800.90. A, which deals with inter-building circuits. An inter-building circuit is a communication circuit that runs between two or more buildings or structures. This section recognizes that running shielded cable underground provides a degree of protection against voltage surges and ground faults. Therefore, if the cable is shielded, grounded at both ends, and the run is less than 140 feet, the code allows for a single primary protector at one end of the circuit, rather than requiring one at each end. In this scenario, a 75-foot underground run from the pedestal to the house qualifies as an inter-building circuit that meets the criteria of 800.90. A. The shielded cable, grounded at both the pedestal and the house, provides the necessary protection, making an additional primary protector at the house redundant. To further clarify, consider the purpose of a primary protector. It's designed to divert high-voltage surges, such as those caused by lightning strikes or power line faults, to ground. This prevents these surges from entering the building and damaging sensitive electronic equipment or causing a fire. By installing the primary protector at the pedestal, the telephone company has effectively created a point of protection for the entire communications circuit. Any surge that enters the cable will be diverted to ground at the pedestal, preventing it from reaching the house. Grounding is a critical aspect of this protection scheme. The shield of the cable must be properly grounded at both ends to provide a low impedance path for fault currents to flow back to the source. This ensures that the primary protector can effectively divert the surge to ground. The grounding conductors must be sized appropriately and connected to a suitable grounding electrode system, such as a ground rod or the building's grounding electrode system. It's also important to ensure that the underground conduit is properly installed and sealed to prevent moisture from entering. Moisture can degrade the insulation of the cable and create a path for ground faults. The conduit should be buried at a sufficient depth to protect it from physical damage. In summary, the installation described meets the requirements of the NEC. The primary protector at the pedestal provides adequate protection for the telephone service, and the underground shielded cable eliminates the need for an additional protector at the house. Remember to always consult the latest edition of the NEC and local codes for specific requirements in your area. When dealing with electrical or communication installations, it's always best to consult with a qualified electrician or communication technician to ensure that the work is done safely and in accordance with all applicable codes and regulations. Failure to comply with these codes can result in serious safety hazards and potential liability. Now let's expand upon the grounding requirements for the shielded cable. The NEC mandates that the shield be grounded at both ends, and this is not merely a suggestion but a crucial safety measure. Firstly, grounding at both ends creates an equipotential bond between the pedestal and the house's grounding systems. This minimizes voltage differences between the two structures, reducing the risk of electrical shock or equipment damage during a fault condition. Secondly, a properly grounded shield provides a low impedance path for fault currents to flow back to the source, as mentioned earlier. This allows the primary protector to quickly and effectively divert the surge to ground, preventing it from entering the building. Thirdly, the grounding conductors used to connect the shield to the grounding electrode system must be sized appropriately. The NEC specifies minimum conductor sizes based on the size of the circuit and the potential fault current. Using undersized conductors can limit the effectiveness of the grounding system and increase the risk of electrical hazards. Fourthly, the grounding electrode system itself must be adequate. This typically involves connecting the grounding conductors to a ground rod, a metal water pipe, or the building's grounding electrode system. The NEC specifies the types of grounding electrodes that are permitted and the methods for installing them. Fifthly, it's important to ensure that all grounding connections are clean, tight, and free from corrosion. Corrosion can increase the resistance of the connection, reducing its effectiveness. Applying a corrosion inhibitor to the connections can help to prevent this problem. Sixthly, the shield itself must be continuous throughout the entire length of the cable. Any breaks or discontinuities in the shield can compromise its effectiveness. If the cable is damaged, it should be replaced rather than repaired. Seventhly, the shield should be grounded as close as possible to the point where the cable enters the pedestal and the house. This minimizes the length of the ungrounded shield, reducing the risk of voltage buildup. Eighthly, the grounding conductors should be run as straight as possible, without sharp bends or loops. This minimizes the impedance of the grounding path and allows fault currents to flow more easily. Ninthly, the grounding system should be inspected periodically to ensure that it is in good condition. This includes checking the grounding connections for corrosion, tightness, and continuity. Any problems should be corrected promptly. Tenthly, it's important to understand that the grounding system is only as good as its weakest link. A single faulty connection can compromise the entire system. Therefore, it's essential to pay close attention to detail and ensure that every connection is properly made. Let's further elaborate on Article 100 of the NEC and its relevance to defining the structure in this context. Article 100 is the foundation of the NEC, providing the essential definitions that clarify the meaning and intent of the code's requirements. It's crucial to understand these definitions to properly apply the code and ensure safe electrical installations. Firstly, the NEC defines a building as a structure that stands alone or that is cut off from another structure by fire walls with all openings therein protected by approved fire doors. This definition is fairly straightforward and generally understood. Secondly, the NEC defines a structure as that which is built or constructed. This definition is intentionally broad and encompasses a wide range of constructions, including buildings, but also extending to other elements that provide support, shelter, or enclosure. Thirdly, the key to understanding whether the pedestal qualifies as part of the structure lies in its function and relationship to the building it serves. The pedestal is not merely a standalone enclosure, it's an integral component of the telephone service for the house. It houses the NIU with the primary protector, which is essential for protecting the building's communication system. Fourthly, the pedestal is directly connected to the house via the underground conduit and shielded cable. This physical connection further reinforces the idea that the pedestal is an extension of the building's service equipment. Fifthly, the intent of the NEC is to ensure that electrical and communication systems are installed safely and effectively. Interpreting the pedestal as part of the structure aligns with this intent, as it allows for a single point of protection for the entire communication circuit. Sixthly, it's important to consider the practical implications of requiring an additional primary protector at the house. This would involve installing another device, potentially creating additional grounding requirements and adding complexity to the installation. Seventhly, in many cases, the pedestal is located close to the property line, making it difficult or impossible to install a primary protector at the house that is both accessible and compliant with code requirements. Eighthly, the NEC allows for flexibility in interpreting its requirements, recognizing that every situation is unique. In this case, the electrical inspector has the authority to determine whether the pedestal qualifies as part of the structure. Ninthly, it's always best to consult with the local electrical inspector to obtain their interpretation of the code and ensure that the installation is compliant. The inspector can provide guidance and clarification on specific requirements in your area. Tenthly, in conclusion, based on the definition of structure in Article 100, the function of the pedestal as an integral part of the telephone service, and the intent of the NEC to ensure safe and effective installations, the pedestal can reasonably be considered part of the structure served. This allows for a single primary protector at the pedestal, eliminating the need for an additional protector at the house. Let's explore the requirements for shielded cable in more detail. The use of shielded cable in inter-building circuits is a crucial element in ensuring the safety and reliability of communication systems. Firstly, shielded cable is designed to protect the signal conductors from external interference. This interference can come from various sources, such as electromagnetic radiation from nearby power lines, radio transmitters, or electronic equipment. Secondly, the shield acts as a barrier, preventing this interference from coupling into the signal conductors and degrading the signal quality. Thirdly, the shield also provides a path for fault currents to flow back to the source. In the event of a voltage surge or ground fault, the shield can carry the current safely to ground, preventing it from damaging equipment or causing a fire. Fourthly, the effectiveness of the shield depends on several factors, including the type of shielding material, the thickness of the shield, and the continuity of the shield. Fifthly, the most common type of shielding is a metallic braid or foil that surrounds the signal conductors. The braid or foil is typically made of copper or aluminum. Sixthly, the shield must be continuous throughout the entire length of the cable. Any breaks or discontinuities in the shield can compromise its effectiveness. Seventhly, the shield must be properly grounded at both ends to provide a low impedance path for fault currents to flow back to the source. Eighthly, the grounding conductors used to connect the shield to the grounding electrode system must be sized appropriately. Ninthly, the NEC specifies minimum conductor sizes based on the size of the circuit and the potential fault current. Tenthly, the shield should be grounded as close as possible to the point where the cable enters the pedestal and the house. This minimizes the length of the ungrounded shield, reducing the risk of voltage buildup. 11thly, the type of shielded cable used should be appropriate for the environment in which it is installed. For example, if the cable is buried underground, it should be designed to withstand moisture, corrosion, and physical damage. 12thly, the cable should be installed in accordance with the manufacturer's instructions and all applicable codes and regulations. 13thly, it's important to avoid sharp bends or kinks in the cable, as these can damage the shield and reduce its effectiveness. 14thly, the cable should be supported properly to prevent it from sagging or straining. 15thly, the cable should be protected from physical damage by using conduit or other protective measures. 16thly, the shield should be inspected periodically to ensure that it is in good condition. This includes checking the shield for breaks, discontinuities, and corrosion. 17thly, any problems should be corrected promptly. 18thly, the use of shielded cable is particularly important in interbuilding circuits, where the cable may be exposed to a variety of hazards. 19thly, by using shielded cable and following proper installation practices, you can ensure the safety and reliability of your communication systems. 20thly, in summary, shielded cable plays a vital role in protecting communication systems from interference and fault currents. By understanding the requirements for shielded cable and following proper installation practices, you can ensure the safety and reliability of your communication systems. Let us elaborate on the specific requirements outlined in 800.90 of the NEC. This section provides the guidelines for protecting communications circuits that extend between buildings. Firstly, 800.90 addresses the protection of inter-building communications circuits from lightning and other voltage surges. Secondly, the primary means of protection is the installation of primary protectors. Thirdly, however, the code recognizes that certain conditions allow for a reduced level of protection. Fourthly, specifically, if the inter-building circuit meets certain criteria, a primary protector is not required at each end of the circuit. Fifthly, these criteria include the length of the circuit, the type of cable used, and the grounding of the cable shield. Sixthly, the code states that if the inter-building circuit is less than 140 feet in length and is run underground using shielded cable, a primary protector is not required at each end. Seventhly, this exception is based on the assumption that the shielded cable provides adequate protection against voltage surges. Eighthly, the shield of the cable is grounded at both ends, providing a low impedance path for fault currents to flow back to the source. Ninthly, the underground installation further reduces the risk of exposure to lightning and other voltage surges. Tenthly, it's important to note that this exception applies only to circuits that meet all of the specified criteria. 11thly, if the circuit is longer than 140 feet, or if it is not run underground, or if it does not use shielded cable, a primary protector is required at each end. 12thly, the primary protector must be located in, on, or adjacent to the building or structure served. 13thly, the primary protector must be listed for the purpose. 14thly, the primary protector must be properly grounded to a suitable grounding electrode system. 15thly, the grounding conductor must be sized appropriately and installed in accordance with the NEC. 16thly, the intent of 800.90 is to provide a reasonable level of protection for inter-building communication circuits while minimizing the cost and complexity of the installation. 17thly, by allowing for a reduced level of protection in certain circumstances, the code recognizes that not all circuits require the same level of protection. 18thly, however, it's important to carefully evaluate the specific conditions of each installation to ensure that the level of protection is adequate. 19thly, if there is any doubt about the level of protection required, it's always best to err on the side of caution and install a primary protector at each end of the circuit. 20thly, in summary, 800.90 provides the guidelines for protecting inter-building communication circuits. By understanding these guidelines and carefully evaluating the specific conditions of each installation, you can ensure the safety and reliability of your communication systems.